Hello everybody, welcome to tutorial 10. Below a dull roar please today, thank you. Okay gang, three little enrichment bits today. This is one of them. You may remember this. I brought this up in class once, and I said I might bring it up again. So very briefly, I'm going to take you on a tour of something. Remember, in this course, you can't take the square root of a negative number, but other people often do. And I is the square root of -1 for people who are allowed to use it. Okay, and I showed you this, and I said it was the most beautiful equation in math, Euler's identity. It's got a bunch of fundamental constants. It's got all the fundamental operations. It brings e and pi and I together in a weird way. And it's simple looking, right? It should be beautiful just on sight. And I didn't explain to you where this came from, so let me just show you where this comes from. Okay? That first equation is just a special case of this mad thing. Okay? So if you go e to the square root of -1 times something, you get this stuff. Okay? And that's how it has to be. There's no other way to make anything work. And you can prove this using series, or you can prove this using derivatives. Possibly, we should be able to do it using the stuff from this course. And this should be amazing because of this, right? The exponentials we've seen, okay, when we've got only real numbers, are either growing or decaying, okay? And yet, where we throw the square root of -1, and there magical stuff happens, and the damn thing becomes periodic, okay? That's crazy. Okay, so something we're used to having go like this or go like this, now does this. It oscillates. It looks like sines and cosines. And this is fantastically useful. So when you want to deal with waves, as a lot of people do, you can use exponentials, which are friendlier than sines and cosines. And so you can just deal with exponentials when you want to deal with waves. And it makes life very, very easy. And a lot of people use this. So don't let imaginary fool you. Use numbers to model things. And imaginary numbers are no different. They make life easy for people who deal with these kinds of things. No, I won't say that. You may remember this from a previous tutorial. We talked about the hyperbolic functions up there, and I said if you know something about complex numbers, those equations may look familiar, and this is why. Using Euler's formula, you can write sine and cosine, normal sine and cosine, in terms of complex exponentials like that. Okay? And that looks a hell of a lot like the hyperbolic function definitions we saw. Okay? Lesson being, if you can talk about complex numbers, if you can talk about imaginary numbers, you broaden your horizons, you get to do a lot of stuff, possibly more easily than you would without them. But in this course, they don't exist. Okay. If anyone can't see the board, I expect a shout. Are there any questions before we move on? Okay. Here we go. Okay, does this look familiar? Okay, we're going to talk about displacement and distance for a second. Or several seconds. Okay, and that's your example. Please, if you can't see, let me know. Familiar theme. An object's velocity v at time t is given by that expression. You want to find the net displacement over that time interval from 0 to 3. What do? D may integrate. Say something, people. Say 0. That'll make me happier than that. Let's do A. Have you seen A Beautiful Mind, where the guy's actually on his own, but he thinks he's with other people? That's kind of what this feels like sometimes. All right, here we go. We're finding the net displacement from time 0 to time 3. Net displacement. Okay, we saw today, and I've mentioned before, you can get net displacement as the signed area under a velocity time curve. So here we go. Integrate over the time interval the velocity. Okay, we did this already today. I wrote the position and everything, so if you want to write it that way, that's cool. Okay, so net displacement being the change in position is the integral of the rate of change of position over time. Okay, and we have an expression. Is it 2 sine pi t? 2 sine pi t. There we go. Okay, antiderivative. You tell me. Yes, ma'am.
Negative 2 cos pi t over pi.
Yeah, cool. Okay, so again, it's continuous. Okay, that's equal to an antiderivative. Thank you. Okay, get some practice with these so you're not completely lost when you have to find one. Okay, if I differentiate, whatever, if I differentiate the whole thing, what happens? Cos becomes minus sine. That minus takes care of that. The pi comes out, cancels that one, and we're left with 2 sine pi t. Good. And then we evaluate and subtract. I'll factor this out to make things look a bit nicer. Cos 3 pi minus cos 0 pi. Okay. Cos 3 pi is minus 1. Cos 0 is 1. Minus 1 is minus 2. Minus 2 times minus 2 is 4. 4 over pi. Okay, so our answer is approximately 1.27. Units? Thank you. All right, there. It's not even exact, to make those of you who are happy who don't like exact things. Okay, that was just the signed area under that curve with respect to the axis. Hi.
Why do you always put the units in square brackets?
I don't know.
It's not a thing.
Yeah, look, I've seen it done. It's like, yeah, some people do it. Yeah, some people do it. The reason I do it is because in math you tend not to write units in places, and so I'm trying to disappear it a little. Is that fair? That's why I did it. Okay. Okay, good. So what does that say? That says that the position changed in the positive direction, so we moved forward, or up, or whatever positive is, that many meters. Okay, and that was just the signed area between that curve and the axis, okay? So it was this area minus this area plus this area. All right. Okay. Now what do we want? We want the position at time 3, given that the position initially was 7 meters. What do we do? Not a trick.
You could just like substitute the values.
Yeah. And then?
Find c.
Yes, although it's a lot easier than any of that. You just, okay, so that was the change in position. That was the initial position. Just add them and you get the final position. Yeah, that'll work. Okay, so net displacement was what? Was position at time 3 minus position at time 0. Okay, so what were we saying here? We were just saying P3 minus P0. I'll write some of this out again so you see it all there. Okay, if I just move this guy over, the final position is the initial position. I say final, is the initial position plus the integral of velocity. Okay, you can get that from this, or you can just think this gives net change in position, and so the final position is the initial position plus the net change in position, and that should make sense. And that's it. Okay, you want to call this final equals initial plus change. Okay. Initial position was plus 7, and we add whatever the heck that was. Let's just do it approximately. Blah, blah, blah. 8.27 meters. Does that make sense? Yes, sir.
So if they make it so convenient in the question, would you like to find C first?
Say it one more time for me.
If they didn't make the question so convenient to what we already thought before,
Yeah.
would we just find C?
You know, I shouldn't have called that C, should I? C means something else first. Do you mean this C? Change. Do you mean that C?
No.
Or that other thing?
I meant, like, for that, I would just.
Yeah, that anti-differentiate thing?
Yeah.
Either way, and that's what I was gonna say as well, which is I think what she was talking about as well, yeah. So parts A and B you can totally do with the anti-differentiating thing, yeah? Which is essentially this anyway. Fair? Yeah, so you can, what do? You've got this guy, you've got that expression, and you can do what we did last week or the previous week, I can't remember. You anti-differentiate that thing to get position, and there'll be an arbitrary constant. If you want to get net displacement, you can just subtract and the arbitrary constant will fall out. And then if you want to talk about B, then you can use position at 0 or 7 as an initial condition, use that to find C, and then you can find, yeah, that's perfect, and that's what you meant maybe? Okay, excellent. Okay, yep, that totally works. Okay. Totally works. Okay. This one I'm tempted to tell you not to fret too much about, but you might as well see it, and because someone brought it up. So here we go, we want to know what distance this guy travels from time 0 to time 3. Okay? So suppose we don't care where we end up relative to where we started, suppose we care about something else. How far did we actually go? You know, how much fuel did we use, how many calories did we burn, or sort of more related to that. Okay, so how much did we actually travel? Okay. And this is how we determine that. I'm not 100% sure this is how the physics people will talk about distance, okay? So if your physics teacher wants you to do something slightly differently, go for it. In that class. Okay, distance traveled from time 0 to time 3 is given by this. Okay, the integral of the speed. Okay, so what's happening here? Again, I'm tempted to tell you don't worry too much, but if you understand this, it's worth it. Okay, what are we talking about here? Let's talk about this a bit sloppily. In a little tiny slice of time, dt, how much do we move? Okay, we move that amount. Okay, speed times time, velocity times time, whatever. But we only care about the magnitude of that, the absolute value of that. Okay, we don't care which direction we're moving in. We just want to know how far we went, and then we want to add up all those how fars to get the total distance. Okay, so we get a bunch of little how fars, add them all up, and we get a total how far. And that's what an integral is. If you want, you can think about it in Riemann sums. Take the limit, and you get the same thing. Okay, so that's that. Okay. Now then. Okay, what does that represent on here? Or do you want to tell me?
Total distance, but not signed.
What's that?
Like the distance but not signed.
Excellent, is that, and that's, yep, excellent. Okay, so it's just a not signed area now. Okay? The unsigned area. So we don't go top stuff minus bottom stuff. We just add. Okay, if you have trouble seeing that, what's going on? If we take the absolute value of that thing, we get this guy. Okay, so everybody underneath gets flipped. Okay, and we're integrating this thing, so we're looking at the unsigned area for this thing. It's always upstairs, so it's the same as the signed area for this thing. Okay, it should be reasonably clear. Let me say that one more time. We're trying to find the integral of this thing, so we're looking for the signed area of this thing. Because it's always upstairs, that's the same as the unsigned area. So it's just the area between the curve and the axis. It should be clear enough to you that the sum of these areas is the same as the sum of those areas. Okay? So what we're looking for is the unsigned area between the curve and the axis. Okay, so you just add up the areas. Okay, so distance is given by the sum of the areas in a VT graph. Or by the area unsigned between the curve and the axis in a VT graph. Okay. This equal sign comes from there. And here's what we're trying to do. Okay. How do we calculate this? Idea? Cases is good. Yeah, pretty much. Absolutely use cases, right? So you can go, okay, over here it's positive, over here it's negative, over there it's positive. So essentially what you do is you break this thing up, right? Because from 0 to 1, we're non-negative. So this guy, its absolute value is just itself. Okay. From 1 to 2, it's non-positive, so its absolute value is negative itself. Okay, and so you can do that. And from 2 to 3, it's non-negative again, so its absolute value is itself. Okay, or you could just go, what we're looking for is the unsigned area. So we'll take that guy's area because it's upstairs, its unsigned and signed areas are the same, it's just that. We want the unsigned area there. Okay, that should just be the negative of the signed area because it's downstairs, so subtract the signed area. And then over here we're upstairs again. And so if we want the area, we just get the integral. Is that cool? Okay, we're just looking for the areas and adding them up. That's all this was. Alternatively, you look at the absolute value function and you think about it that way. Okay, I'm lazy, this thing's symmetric, so I'm not going to do 3 of those guys separately. I can see that that area is equal to that area is equal to that area, so you know what, in this case I can just say it's 3 copies of this thing. Okay? And then we just calculate that. And again, this brings together stuff you saw much earlier on about absolute values, brings it together with the stuff we've done recently. To answer a practical question. Okay. Good. Okay, I won't ask you again, you've already given me the antiderivative of this thing, or an antiderivative of this thing. It's 6 over pi cos pi t 1, 0. Okay, before we had minus 2 over pi, multiplied by 3, you get minus 6 over pi. And that's that. Okay? Questions? Same as before. Okay? Just in this case, we care about area, so we break up into cases, essentially. Or we break up the interval of integration into subintervals. Okay. So minus 6 over pi. Cos pi 1 minus cos pi 0. That's minus 1. That's 1. Minus 1 is minus 2. Minus 2 times minus 6 is 12. So we get 12 over pi. Which is approximately 3.82 meters. Okay, and notice that is bigger. First of all, notice it's positive, it had better be, right? If you're integrating, an absolute value, you get something that's negative, you've got a problem. it's positive and it's bigger than the net displacement we had, one hopes, right? Because there were no cancellations this time, you're just adding up the total distance traveled. Okay, so you should get something bigger than the net displacement. Because there were cancellations in the net displacement. Okay? Okay. I didn't bring this up because it's vitally important necessarily. I brought this up because a question came up. I brought this up because it appears in books frequently. And because this is a practical sort of question and something you might want to ask. How far did I go? I don't really care where I ended up and where I started. Okay, if you have questions about any of this now or later, ask. Okay? Okay. Okay, my second attempt at engagement. Okay, an application, people. This is a real application. Whenever you see something about this, you'll see an integral sign. You'll see an integral sign in a biology place, which is always a shock to everybody. Okay, pneumotachometry is how I'm going to pronounce that. Okay, pneumo being air, tacho being speed, metry being measurement. So if you want to measure the lung function of a person, okay, you might get them to breathe into one of these things. Okay, and what this thing measures is airflow. Okay, so the volume rate of flow of air through this thing. Okay, you breathe into it, breathe through it in and out, and it measures that rate of flow. Okay, and it measures it in a funny way. It measures a pressure difference somewhere, turns that into a voltage, turns that into a flow rate. And what it spits out are pneumotachograms. Okay, and so this is the flow rate of air over time. Now the thing is, if what you care about is how much air has been moved, so the net movement of air, or you care about how much air is in the lungs at this moment, that's not all you need, right? That's the flow rate. To get the amount of air moved, or the volume of air in the lungs, you need to integrate. It's one of these things. It's net change is equal to the integral of the rate of change. Okay, so for that example, pneumotachogram, you'd say something like this. The net change in volume of air is equal to the integral over time of the volume flow rate of air. Okay? And so if you're up to that kind of thing, you could fit a function to this and then integrate that function, or more likely what you're going to do is you're going to numerically do something. You're going to put rectangles under it, add up the areas of the rectangles, trapezoids, something like that. Okay. Good? And what I said about units should make sense. We talked about, okay, this thing is in liters per second. T is in seconds. You multiply them, you get liters, and that's units of volume. So life's good. Okay. Questions? Good. If I do manage to run out of questions, I'll dig up more. Let's talk about integrals for a bit. Everybody's good? Okay. All right. I'll call this integrals, although that's what we've been doing anyway. Okay, let's do some stuff. Okay, find me this. The derivative with respect to x of this thing, the integral from -6 to x of e to the t squared dt. I promise it's easy. Ludicrously easy. Who wants to tell me what to do? Part 1 of the fundamental theorem told us what? Oh, hello, what?
Find the integral.
See, this is one of those ones where you can't. And I put that there intentionally, that you can't write a nice antiderivative of this thing. It's literally impossible. You go ahead,
Since the derivative and the antiderivative are opposites,
yeah. Mm-hmm.
doesn't it just end up being like ex squared?
That's it. Easy as that. It couldn't be any easier. That's it. Okay? If you remember part one of the fundamental theorem, it told us what? It told us that if we get the area so far function up to x, okay, so from any constant up to x of a continuous thing, and we take the derivative, we just get that guy back, evaluated at x. Okay? So if you look at the fundamental theorem part one, it looks almost exactly like that. And that's all we did.
If there's a number in front of p, would it just go in the denominator?
Where are we talking about? Here?
Yeah.
Well, that would be part of the function, you can just stick it there. Like, there's no anti-differentiation going on at all. You don't have to think at all. You just see this, and you can think what she said. You can think that differentiation and anti-differentiation, or sorry, differentiation and integration are opposites, and so you recover the function. That works. Okay, so if you just look at part one, it looks almost exactly like that. And I could conceivably just dig it up. At the risk of you seeing all my secrets. Aww.
Oh, there we go.
Good. It takes that long for light to travel. Okay, there you go. Literally, okay? So we have something that looks like that. We take the derivative with respect to x, and we just get the function inside there, the integrand, evaluated at x. That's all that is. Okay? So if you ever see a question like this, you should be very happy. Okay? It's a gift. That's not a hint. I'm just saying that if you do, you should be happy. Me saying it's not a hint is also not a hint, all right? Seriously. Not a hint. Okay. All right. We're good? Okay. Now it's a bit hairier. Let's see what happens. And again, yeah, if you tried to find an antiderivative of this, good luck. In a nice form. Okay. It's almost the same, but not quite. There's a problem. What do you want to do? You want to say, do the same thing. You want to say cos x cubed. But it's not quite that. Okay? We're differentiating with respect to x. This guy ain't x. So we got a problem. So,
To third root the whole function?
say that again?
Do you have to cube root the whole function?
No. I'll do something more systematic than that, we'll see. Yeah. Nothing creative. I'll just do literally what I learned and then we'll, yeah. I can't justify doing that. Look at this guy. What function do I want to call this? This is the area from, if we use the notation I used before, it's the area from 1 to x cubed. That looks like a composition to me. It's a function of a function. Okay? Okay, that's the area, that's how I write the area from 1 to this thing. Okay? Again, we're looking at a function of a function of a function of x. And x is what we're differentiating against, so that's what matters. And so we have to use chain rule, crazily. Okay, so the derivative of the outside, evaluated of the inside, times the derivative of the inside. Okay, again, because this guy is a function of x. And I can't imagine anybody seeing this, getting this the first time. It's just nuts. Okay? Now this guy's familiar, okay? So the derivative of, let's write this.
That's getting a little low.
It's getting lower, it is low. All right, here. This is the outside function. All right, don't get too bent out of shape over this, all right? This is, I don't know, yeah, this is mainly a sort of fun example. Okay, so we're talking about the area from 1 to u. Okay, this is the outside function, the inside function is x cubed. Okay? Okay, now the derivative of this guy with respect to its argument is indeed this thing evaluated at the argument. Okay? So FTC part 1 tells us this. Okay, tells us if we differentiate that, all we have to do is evaluate that at the argument, and that's what we get. Okay? Okay, so that's the outside function dealt with, and its derivative. So we take the derivative of the outside function, evaluate the inside, and then take the derivative of the inside. And that's the answer. Okay? All right. What am I staring at? That's the question. Okay, is that reasonably sensible? Yes, ma'am.
Can you explain that briefly one more time?
Yeah, sure. Okay. We want this, okay? If we had had a constant of going up to x, life would be good. We just stick x in here and everything would be fine. Okay, but this isn't x, it's something else. Okay. If we call this kind of thing, this area from 1 to thing function, okay? If we look at it as a function, we're trying to find the derivative of that at x cubed. Right? We're trying to find the derivative of this, the area from 1 to x cubed, which is a composition of the area so far function and this function. Okay? And then it just becomes chain rule. You can just write chain rule for something like this, you get something like this. And now the derivative of the outside is easy. It's just what we did before. The outside function is just an area so far function. Take its derivative, all you have to do is plug into the integrand. Weird, yeah? Yeah, okay.
So that's basically just like substitution, right? Like you just like put the u and then you substitute it.
What's that?
So like wouldn't that just be like substitution? Like you took the u and then you just substituted it exact.
Oh, that kind of substitution? The one we haven't seen, right? No, because that kind of substitution, usually you're talking about the integrand. U something equals something in there, right? This is a bit different. Again, just try to see that, okay, this isn't just simply from 1 to x. It's from 1 to a function of x, okay? So it's a composition of the from 1 to something area function and the x cubed function, okay? It's a composition of those two. When you got a composition, you have to use chain rule. Okay, and the derivative of the area so far function, we do just as before. And because of chain rule, we just have this extra piece. I appreciate this is ridiculously hard to see sometimes.
Should we be differentiating codes? So shouldn't it be?
No.
No? No.
Because of the magic of fundamental theorem stuff.
Oh.
To be honest, if you had something like this and you're just totally confused, what can you do? This thing has a nice antiderivative, find that, evaluate this, take the derivative, and you don't have to think about any of this. Yeah? Because this guy's nice. You could just, put with sign and then life's good. Yeah, that'll work just fine. Okay? This is more direct if you can see this. And it always works. Okay. Again, look for an outside function, look at the inside function, use chain rule, that's all this is. outside function, inside function. And please don't panic over that more than it deserves to be panicked over. But everyone in calculus sees that, and so you deserve to see it. Okay. Let's do more normal things. Integrate from minus e cubed to minus 2e. 3 over x dx. And you go, why are there e's there? That's a bit of a hint, and it is. All right, team, what's an antiderivative of this thing?
3 times LNS.
Thank you, and thank you for saying that other bit. Excellent, okay? Again, always gonna ask, make sure this is continuous. Okay, we're mean if we give you something that isn't. Make sure this is continuous on the interval, it is. And an antiderivative is indeed, like you said, that. I picked this interval so that for once this absolute value would do something. Minus 2e minus e cubed. And then just run it through. Minus 2e is a negative number. So I can write that. Minus e cubed is a negative number. So I can write that. Is that okay so far? All right. All right, people, what's ln e cubed? What exponent do I have to raise e to get e cubed? Not everything has to go into the calculator. Okay? Or you bring the 3 down and you see the ln e is 1. Okay? Do this however you want. You can say this is ln 2 plus ln e. Okay? So it's just ln 2 plus 1. Okay? 3 ln 2 plus 3 minus 9. One more time. 3 ln 2 plus 3 minus 9. Okay? Again, if these guys had been positive, then you wouldn't have needed the absolute value, and forgetting it wouldn't have done you any harm. But here would have done you harm. Questions? Okay. Who's next? Go from 1 to 3, dx over x squared. Okay, antiderivative of 1 over x squared. Or x to the minus 2. Help me.
Minus 3.
Oh, thank you. What's that? Other way.
X minus 1.
That's it. Yeah?
Yeah.
The minus 1, is that what you said? I think, is that, okay, cool. Yeah, okay, so what is this? This is x to the minus 2, so when you want to anti-differentiate, you crank up the exponent and divide by the new exponent. Yeah? So you get x to the minus 2, you crank it up to x to the minus 1, and you divide by minus 1. So you get this. Okay? Okay, x to the minus 2, you want the antiderivative, crank up the exponent by 1, divide by the new exponent, as we've said before, and you get this, minus x to the minus 1. All right, evaluate. That's 1 minus a third, that's 2/3. Okay, what sort of thing are we looking at here? 1 over x squared looks like, sort of, like this. And as we integrate from 1 to 3, we're finding that area. Okay, good, it's positive at least. Yes, ma'am.
-4 was
What's that?
Wait, should that be -4?
No, you're supposed to add them. Are you not?
No, it's subtract.
Is that cool? Minus a third,
Right.
minus 1 over 1. So it's 1 minus a third, so 2/3. Cool? Is that? All right. Okay. Let's do this. Okay, if I've got this, same integrand, same antiderivative, and I do this. Okay, same antiderivative, I've just changed the interval. 1 and minus 1, let's do this again. So we got minus 1 over 1, minus, oh God, 1 over minus 1. All right, what do we got? Minus, 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 that's 1 minus. So it's minus 1 minus 1. Well, that's interesting, isn't it? So what have we done? We had a thing that looked like this. I've integrated it from minus 1 to 1, and I've told myself that that area is minus 2. There we go, and that's the answer to your question. Sometimes it matters. Okay, this thing was not continuous, I didn't check, and now I am. Okay? No. Okay? The integrand was not continuous on the interval of integration. The fundamental theorem did not apply. Okay? So if someone wants to screw you over, that's the kind of thing they do to you. The problem with this guy is it's not even integrable. There's no way of calculating that thing that just doesn't exist. Okay? That integral doesn't exist. Okay? And remember I said that you definitely are integrable if you've got a continuous function or you've got a function that's continuous almost everywhere and everywhere else. It's continuous almost everywhere, and where it's not, it's just got jumps and removables and finitely many of them. Something like that. Okay, so it's got to be reasonably well behaved. If the function blows up, it may or may not be integrable. And by our definition, it's not, period. Okay? If you take 128, you'll talk about some cases where the function blows up, but you can still talk about a sensible integral. But not here. What's that? Yeah. It involves limits. Yes, ma'am?
If you integrate a circle, do you get 0? Or is that...
In where?
If you integrate a circle,
Okay. Circle, like here.
you just get 0, right?
What are we, yeah.
Oh.
Yeah, if it's there. Yep, yeah. Good. Okay, so again, the problem there was that the thing wasn't continuous on the interval. And in fact, it's worse than that. There's no way of calculating this integral. It just doesn't exist. And that's it. FYI, FYI, please please don't fuss over this. I said that it's okay to have finitely many jump and removable discontinuities. For example, sort of, kind of, if we had something like this. You can get a sensible signed area out of that. You go minus this area plus this area. Okay, so it's discontinuous, but you can still make a decent integral out of it. FYI. Okay? All right. All right, let's upset some people. Find me this. And I don't know yet if we expect you to have these memorized. But maybe it'll be familiar to somebody. Anyone know what has that derivative?
Yeah.
That could be the whole answer. And that does answer the question. That's very close.
Arcos.
The arctan.
Arctan.
I think arcos is a root. Yeah.
Yeah, that one.
Yep. Excellent. That's it. Okay. Keep it down, nation. Tan inverse arctan, write it however you want. Okay, insanely, at some point we learned that if we differentiate arctan, we get 1 over x squared. Sorry, 1 over 1 plus x squared. Okay, I think we used implicit differentiation, yeah, to deal with that kind of stuff. Okie dokie. So evaluate as usual. By the way, yes, it's continuous where it needs to be. Well spotted. Okay, what's the arctan of root 3? Just start guessing special angles and I'll tell you if you got it.
Pi over 6.
Keep going. I think, yeah, possibly. Did you say 3 too?
I said 3, yeah.
3 is good.
No one has said it. You're so said that.
All right, good. All right, very good. Right, okay. Pi over 2 is very bad. Right, but not very bad, but you know what happens. Yeah, bad things happen in pi over 2 and tan, that's what I meant. Not that the answer was very bad. And in pi over 4, you've got tangent 1. Yep. Okay, arctan 1 over root 3. That's good, thank you. Excellent. And by the way, this is seriously weird, okay? It is weird that if I get the area under this thing from here to here, I get pi turning up. That's just nuts. All right. You might as well see this, verify. Okay. The indefinite integral of ln u with respect to u. Okay, lunu du, ulunu u. Take a music class, and that's what it all sounds like. Okay. Excellent. Verify that. What do you have to do to verify something like this? Differentiate that baby and get this. Yep. Okay? Like if I just asked you to find that, you'd have probably gone, that's weird how, and I'd agree with you. Okay? But if I told you this, you should be able to check it. So let's check it. Ooh, no. All right. Product, derivative of first, times second, plus first, times derivative of second, and now derivative of u with respect to u is 1, and the c goes away. Okay, that's just 1 minus 1, and we're left with London. Cool? Nice hiss there. Okay, so if you ever have to check one of these things, either because you did one or because someone asked you to for some sick reason, you take the derivative and you better get the integrand. Or it's like when Dory was talking to the whale, if you've seen that. That's it. Very good. Escape. All right, let's do this one. You've seen this or something that looks like it before, I think. If it was this bad, you wouldn't be doing it right now. What could possibly save us here? Hint, look for an identity. Hint, factor something else. Huh? Factor out sine of x, that's good. So you factor out sine of x, and then let's just look at that side.
And then you can have.
Go ahead. Yes, sir.
That equals 1.
That's good. And so we have something nice, don't we? So all it wound up being was this. And someone was just trying to make you dizzy. All right, what is that? What's that answer?
Cos x plus c.
Excellent. Good. Minus cos. Okay, if it was cos, you'd get minus sine. So you put minus cos, so you get sine. Don't forget the c. Unless I've forgotten it. Okay. Okay, again, please don't fall into the trap. If someone gives you something like this, don't give me something with a C on the end. If someone gives you something like this, don't give me a number, okay? Make sure you've got the indefinite and definite straight in your head. Okay, another weird one. Presumably the really easy ones you can do really easily on your own. So we'll do another weird looking thing. Okay, this is one of those things I wouldn't be smart enough to figure out the first time I saw it. If you can, well done. Otherwise I'll tell you what to do. Again, hint identity. Yes, ma'am. This one? Yeah.
Can we like take out sin x completely out of Point Pico and put it like outside?
No, because it's a function of this thing.
Okay, so like it has to be.
Yeah. If it's not a function of x, then you can do whatever. Yeah, you can pull it out.
Like if it doesn't have x.
So if it was like 2
constant.
or 3y or something. If it, no, not 3. Okay.
The constant basically.
Yeah, constant. Yeah. Let's just say a constant, and that's good enough. Yeah. Okay. Again, I'm not clever enough to see this if I hadn't been told how to do this. So. You may remember this thing. That was an identity at some point. And you can rearrange that to get this thing. One second. And I think something like that showed up on the last page of your exam or your midterm. Okay? Or you may have seen this as cos squared x minus sine squared x, and then you use the Pythagorean identity on top of that and you get this thing. The point of this is that sometimes identities are useful. So if you've got something you don't know how to deal with, identities can be useful. And this does come up. Okay, does this make our life easier? If I use this here, does that make my life easier? Okay? Let's go. Okay, 1/2 minus 1/2 cos of what? So let's, 6x is good, okay? So my x here was 3 theta, so my x here was 3 theta, so 6 theta. If you want, try this first with just sine squared theta, and then try it with sine squared 3 theta. And from there, it's the usual stuff. Okay, antiderivative of 1/2 with respect to theta. Yeah. Okay, this thing.
Negative 1/12 sine 6 theta?
That's it. Yeah, that's it. If I took the derivative of this, what happens? I get cos 6 theta, the 6 comes out, it goes over here, you get minus 1/2 cos 6 theta minus 1/2 cos 6 theta. What am I missing? C. It's a high school thing to do, there we go, C. Okay. Incidentally, guys, we did antiderivatives at some point in a previous tutorial, possibly last week, possibly the week before. All that stuff is legitimate practice for this as well, because that's all this is. Okay, so if I said find the general antiderivative, that's the same as asking something like this. Okay, so have a look at that. All right. Okay, something to think about. Something to think about before Wednesday. Think of me. I said that this was bad news. This isn't bad news. Think about what you'd do. Think about what the antiderivative of that might look like. If you already know, tell me. Otherwise, just think about it. We'll talk about this kind of thing on Wednesday.
So you just like substitute.
Yeah, it is just substitute. That's right. Okay. Why would this be here? And what's its relation to this? Just think about it. We'll talk about more of that stuff on Wednesday. Any questions? Okay. Okay, we're gonna have a chat where you can tune out. Okay, who's seen this? In 150 or somewhere else?
Yeah.
150, okay. Okay. Look how cute they are. Okay. So I brought this up before. A long time ago I mentioned this, possibly when I was talking about periodic functions, possibly when we were talking about when you can invert things. Give me 1 second. Okay, yeah. I brought this up in this course, possibly when we were talking about periodic functions a long time ago, or when things are not invertible. This is in the Arctic of this country. That's a snowshoe hare, that's a lynx, and that guy loves to eat that guy. And the populations of these things oscillate over time, okay? And one lags behind the other. And I think those in ecology will have seen something along those lines. That's what this is. I think these are collected pelts or something like that. You can just think of these as populations. And you can see the populations are oscillating, okay? So you could, I can't remember what the final explanation in ecology was, but one explanation you could give is essentially that when you've got, let's see here, if the population of lynx is high, they eat the hares, the population of hares goes down, and then the lynx are in trouble because there's nothing to eat, so the population of the lynx goes down, and then the hares go, oh good, we can live now, and so that population goes up and on and on and on, it oscillates, okay, with a lag. Okay, now the question is, can we do anything with this mathematically? Okay, this is a famous set of equations, so it's worth you seeing this. Okay, so if we have just prey, so just the bunnies, and there are no cats around, hares and lynx, they're in good shape, okay? So let's suppose that they thrive. Let's suppose that they can grow exponentially, and that's what this is, right? It's the natural growth law, okay? So let's suppose that if there's no predators around, the prey can just blow up exponentially. Okay, let's suppose that if there's no bunnies around, the cats are in trouble. There's nothing to eat, okay? And so their population decays. This is a natural decay law, and their population just decays exponentially to nothing. Now the question is what happens when you bring them together. Now we've talked about one population at a time. We've talked about exponential growth and decay. We've talked about logistic growth. But we've never talked about what happens if there's two populations. Okay, if these guys are both there, what goes on, okay? The cats eat the bunnies, okay? That's trouble, minus sign for the bunnies. And it's good, plus sign for these guys, okay? So the growth rate of the lynx benefits from the predation. The growth rate of the bunnies suffers from the predation, okay? Now that effect, you could say, is proportional to how often these guys run into each other, okay? And you could say that how often they run into each other should be proportional to each of their populations, okay? So it makes some sense to say, well, the more cats there are, the more often they interact, the more bunnies there are, the more often they interact in a sort of proportional-ish way. And this kind of thing, where you say the effect is proportional to each of them, and so it's proportional to the product of them, is called law of mass action. And you may have seen this in chemistry, where you talk about molecules reacting, right? The frequency at which the molecules come together might be proportional to the product of their concentration. Okay. So I think in elementary reactions that are first order, the two reactants, you would have seen something like that. There you go. So this kind of thing is called mass action. Okay? And look at what we've got now. These things are tied together, okay? Because the differential equation for the cat has got cats and bunnies in it, and then the differential equation for the bunnies has got bunnies and cats in it. So these guys are tied together. And it turns out this does do something. This does show oscillations, okay? With a certain set of parameters, a certain set of values, you get a graph that looks like this, okay? So what do we got? Blue is bunnies, red is lynx, okay? And we get oscillations, and we get a lag. And so this kind of thing does actually predict what we want it to predict. So that's interesting. So a decent mathematical model, or actually a fairly simple mathematical model, gives you the kind of behavior you'd expect. Or not expect if you didn't know that these kinds of oscillations happened. This isn't necessarily a useful thing for predicting like numbers, okay? But it's good for noticing patterns. It's good for trying to come up with underlying reasons for things. These are called the Lotka-Volterra equations, the ones on the previous slide, and these came up initially when they were thinking about fishing in the Mediterranean. And again, you saw oscillations there. And one other observation that happened is as the less they fished, the higher proportion of predatory fish they caught, which is a weird thing, okay? And the mathematical model can predict that, okay? So this is a nice thing about models. You come up with something, it's rigorous, and you can test it, okay, with predictions like that. Okay. One problem with this model is it's a bit too simple, and if you try to make certain realistic changes to it, for instance, you try to make the growth of the bunnies logistic, you stop having these cycles, okay? So it's not structurally stable. So you have to do other changes. You have to model the predation differently. You have to model something like the Ali effect, if you've heard of that, not named after me. And if you do that, then you get something structurally stable. Then if you add little bits of realism, then you still get oscillations. Okay, so this is just an example of a model from theoretical ecology that has had some success, and there's lots of extensions to it. And that's that. Okay. That's all I had to say. If you want, I'll answer anything you want me to answer, or I'll just pull something out of any of these 3 books. Otherwise, I'm happy to call it, and anyone who has any questions can talk to me. Thank you. I like how you go silent now. Again, if anyone feels ripped off, I'll just keep doing stuff. More than happy, and I have more than enough books. Otherwise, you get to go home or talk.